The atom as a tiny solar system, a nucleus like the sun, with electrons orbiting like little planets.
Right. It's a really common picture.
And it's useful, yeah, to start with, but when you actually deep dive into modern physics, specifically quantum mechanics, the reality is, well, it's a lot weirder.
It absolutely is.
Yeah.
That classical planetary model, it feels intuitive, but it just doesn't hold up at the atomic scale. Quantum mechanics basically throws out those neat, precise orbits.
And replaces them with something else entirely. The electron cloud.
Exactly, the electron cloud.
The cloud, which, sounds kind of soft and fluffy, but isn't really physical fluff, is it?
Not at all.
And the sources you shared for this deep dive, they jump into a really thought-provoking question about this quantum cloud. Can this electron cloud actually be understood in some sense as an energy field?
That's the core question your material is tackling. It's a conceptual deep dive. Yeah, analyzing exactly that connection, pulling insights from both quantum mechanics and field theory. It really forces us to look at electrons and their energy in a way that kind of breaks from our everyday intuition.
Oh, okay. So our mission in this deep dive is to really wrestle with this idea. We want to see how electron clouds connect to energy fields, through the lens of modern physics, and understand why looking at electrons this way might actually matter. So yeah, let's get into it.
Sounds good. First things first, let's make sure we're on the same page about the electron cloud itself. The big shift, really, from classical physics to quantum mechanics is key here. Instead of picturing a definite particle, like a tiny ball following a set path, the electron's location in an atom is described using probabilities. It's fundamentally probabilistic.
So the cloud isn't like a physical mist or fog, it's something less tangible.
Exactly. It's a probability distribution. Think of it like a map, maybe. Oh. Yeah, where the density of the cloud at any point tells you how likely you are to find the electron right there. It's smeared out. The electron isn't fixed to one spot, but its probable location is spread out over a region.
Right. And this probabilistic behavior, the smearing out, it's all captured mathematically by something called the wave function, that Greek letter psi that you always see.
That's the one. The wave function is the mathematical object that describes the electron's quantum state. And the crucial bit for visualizing the cloud is that the square of its magnitude, that's ek, gives us the probability density.
Probability density, okay.
So where ek is high, the electron is more likely to be found. Where it's low, it's less likely. Simple as that. Well, conceptually at least.
Which gives us those famous shapes, doesn't it? The atomic orbitals, the S, P, D, F shapes you learn about in chemistry. They're not orbits, they're pictures of this probability density, where the cloud is thickest.
Precisely. Those specific shapes, like the sphere for an orbital or the kind of dumbbell shape for a orbital, they directly show the regions where the electron's probability density is concentrated. And this really highlights that concept of delocalization. The electron's probable location isn't a single point. It's spread across a whole volume.
Okay, got it. So, electron cloud, probabilistic, delocalized map, shows where the electron is likely to be found, all governed by the wave function. Now, the other side of this coin is the energy field. What are we talking about there in physics terms?
All right. So an energy field in physics is essentially a physical quantity that exists throughout space and time. And crucially, it stores energy, and it can transmit energy, too.
Okay. And what are its key features? What makes something a field?
Well, first, it has a spatial distribution of energy. The energy isn't just at one point. It's spread out over a region. Fields also often mediate forces. Like, the electromagnetic field mediates the forces between electric charges.
Makes sense.
And they have an energy density, meaning you can talk about how much energy is stored in a particular volume of the field.
Right. And we know some classic examples like the electromagnetic field. Generated by charges, carries light.
Absolutely. That's the textbook example. It carries electromagnetic energy, mediates those forces, and light is just a wave traveling in that field.
And the gravitational field, that's another one, generated by mass, mediates gravity.
Yes. And then, jumping into more modern physics, we get quantum fields, QFT, quantum field theory.
QFT, okay.
This is where things get really interesting. In QFT, the fundamental particles we know, electrons, quarks, photons, they aren't seen as tiny point-like balls anymore.
They're not. So what are they?
They're seen as excitations, like localized ripples or vibrations.
Vibrations in what?
In fundamental fields that fill all of space-time. There's an electron field, a photon field, and so on. The particles are the excitations of these fields.
Wow. Okay. So electron cloud, probability map for location, energy field, region storing and transmitting energy. Now, before we try to properly connect the cloud to a field, the source material makes a really critical point. Electrons, just by existing, inherently have energy.
That's absolutely fundamental. An electron isn't just sitting there waiting to be found. It carries energy with it. And your source breaks down the types pretty clearly.
Like what?
Well, there's a kind of kinetic energy, although picturing motion in the classical sense is a bit tricky for something delocalized like this.
Right, because it's not zipping around a track.
Exactly. Then there's potential energy. For an electron in an atom, that's mainly the electrostatic potential energy, its attraction to the positive nucleus and repulsion from any other electrons nearby.
Okay, kinetic and potential. Anything else?
And of course, its intrinsic rest mass energy. The
Yeah.
famous EBA told you that energy is inherent to its mass.
So if the electron cloud shows where the electron is likely to be, does that mean it's also showing where all this energy, kinetic, potential, rest mass is likely to be concentrated?
Precisely. That's a key insight. The regions where you're more likely to find the electron particle are inherently the regions where the energy it possesses and contributes to the atom is, well, predominantly located. The probability map for location is also, indirectly, a map for where its energy resides.
Okay, this is where it gets really interesting, connecting these two ideas. Your source explores what? 3 main ways we can bridge the concept of the electron cloud and the idea of an energy field. Where should we start?
I think the most direct way is to just remember that an electron carries an electric charge. That's fundamental.
Right, it's negatively charged.
And any charged particle automatically generates an electric field around itself. That's just electromagnetism 101.
And an electric field is a type of energy field, right? It stores energy in space.
Exactly. It has an energy density spread through space. So the electron cloud, by telling us where the source of this electric field, the electron itself, is probably located, it's also telling us where the energy density of the electron's own immediate electric field is likely to be strongest, most concentrated.
So if the electron's probable location is spread out, fuzzy.
Then the energy associated with its own electric field is also kind of spread out in that same region. The cloud maps the likely source and thus the likely concentration of its field energy.
Okay, that makes intuitive sense. Where the electron probably is, its field is strongest, and that field holds energy. Okay, what's the second connection the source highlights? This one feels a bit more quantum.
It definitely goes deeper into the quantum description. The wave function isn't just about probability, it's deeply connected to the electron's energy. Your source points out something crucial. The total energy an electron possesses when it's in a specific orbital, like an S or P orbital, isn't just any old value. It can't be.
It can't.
No, it's a fixed, quantized value. Energy comes in packets at this scale.
Quantized, meaning only specific discrete levels are allowed, like steps on a ladder, not a ramp.
Exactly. This energy value is what physicists call an eigenvalue. It's one of the specific allowed energy solutions when you apply the Hamiltonian operator, which is basically the mathematical tool representing the total energy of the system, like the atom.
Okay, hold on. Hamiltonian equals total energy operator. Eigenvalues, the specific allowed energy levels that come out when you solve for the electron in the atom.
You got it. And the wave function, which gives us the cloud shape, corresponds to one of these specific allowed energy eigenvalues.
Ah, I see. So the cloud, which maps the spatial extent of that specific wave function?
Isn't just mapping where the electron particle might be found, it's mapping the physical region where this specific quantum of energy, this allowed eigenvalue energy associated with that electron state, is actually manifested or localized within the atom.
So the cloud indirectly shows where the electron's specific contribution to the atom's precise quantized total energy is located.
Exactly. It's a spatial map for that specific energy state.
That's a different way to think about the cloud. Not just location probability, but the space where the energy of that state exists.
Yeah.
And the third connection, the one using quantum field theory. That sounds like the deepest level.
It is, arguably. This is the most profound perspective the source brings in, and it really shifts how you think about particles fundamentally. Remember how we said QFT views particles as excitations of underlying fields?
Yeah, like ripples in a field that fills space.
Right. So in QFT, the fundamental things aren't the particles themselves, but these quantum fields that permeate all of space-time. There's a fundamental electron field, a photon field, a quark field, etc.
So an electron particle, from this viewpoint, isn't a tiny ball flying around. It's more like a persistent, localized excitation or vibration in this underlying electron field.
Precisely. An electron is a quantized excitation of the electron field. Think of it like a stable note being played on a string that extends everywhere. And crucially, these excitations, these notes, inherently carry energy.
Okay, so how does the electron cloud around an atom fit into this QFT picture?
Well, from the QFT perspective described in your source, that cloud around an atom can be seen as a localized, stable pattern of excitation. It's a specific way the electron field is vibrating or excited right there. And it's sustained and shaped by the influence of the nucleus's potential field.
So the nucleus kind of plucks the electron field, causing a stable excitation pattern nearby.
That's a decent analogy, yeah.
Yeah.
And this excited state, this pattern, inherently contains energy specifically, the quantized energy levels, the eigenvalues we just talked about. So in this view, the electron cloud is a region where the energy of this localized excitation within the broader electron field is concentrated.
Wow. Okay, that really does flip the script, like you said earlier.
It does.
Instead of thinking of a particle, the electron, which has energy and has a field around it.
The QFT view suggests the field is fundamental, and the particle and its cloud is a pattern of concentrated energy in that field.
So it changes the perspective from an object in space to something that is a configuration of the field filling space, an energetic configuration.
Exactly. The QFT viewpoint makes the link between the electron cloud and the energy field concept incredibly direct, almost inherent. The particle is an energy excitation of its field.
Okay, so the connections are pretty compelling. The cloud maps where the electron's own energy, kinetic potential, its field's energy, is likely found. It maps the region where the specific quantized energy associated with its wave function state is manifested. And fundamentally, in QFT, it is a region of concentrated excitation energy in the underlying electron field. But as your source rightly emphasizes, we need to be careful not to just slap a classical energy field label on it and call it a day. There are important nuances, right? What are the key distinctions?
Yeah, that's vital. A primary one is that the cloud is first and foremost a probability density map for the electron's position. Where is it likely to be? While that strongly correlates with where its energy is found, it's not strictly a direct map of energy density in the classical sense, like joules per cubic meter in an electromagnetic field.
Got it. Probability of finding the electron versus amount of energy per unit volume. Related but not identical maps.
Right. Another distinction mentioned is that the electron cloud in an atom usually describes the state of one specific electron, or maybe a few. Classical energy fields, like the EM field from a radio tower, can exist more independently or be the collective result of zillions of charges. You can measure the field's energy density way out in space, far from any single source.
Although, like you said, QFT kind of fuzzes that line a bit, since the particle is seen as part of its own field.
It does blur it, absolutely. And maybe the most critical quantum feature is quantization. The energy of the electron bound in an atom can only exist at those specific discrete levels we talked about. The electron cloud represents one of these stable, allowed quantum states. Classical fields don't typically have that inherent discrete energy structure in the same way.
Which brings up a fascinating point. If the electron is an excitation of a field, like a vibration, how does a continuous field end up having these very specific quantized energy states when it's bound inside an atom? How does the field excitation become quantized?
Well, that's one of the triumphs of QFT. It actually explains that. When you apply the rules of quantum mechanics to the field itself, and you consider the field being confined or influenced by a potential, like the nucleus, the excitations of that field naturally become quantized.
So the confinement forces the field's vibrations into specific allowed patterns.
Essentially, yes. The allowed stable excitation patterns, the modes of the field when bound by the nucleus's potential, can only exist with those specific discrete energy values. The electron cloud in a specific orbital is, from this perspective, a visual representation of one of these stable, quantized excitation patterns of the electron field shaped by the atom's environment.
Okay, so what does this all mean? Let's try and pull everything together from your source material. The big takeaway seems to be that while the electron cloud is fundamentally about probability of location,
Yes.
it's also deeply and meaningfully linked to the concept of an energy field. It's not just about location.
Absolutely. It effectively outlines the region in space where the electron's inherent energy, whether you think of it as its kinetic and potential energy or the energy stored in its own immediate electric field, is most likely concentrated.
And perhaps most fundamentally, especially if you take that quantum field theory perspective seriously,
Mm-hmm.
the cloud is a localized, stable excitation of the underlying fundamental electron field itself, which makes it a region of spatially distributed energy in a very profound way.
Exactly. So within the whole framework of quantum mechanics, thinking of the electron cloud as serving a role similar to an energy field in the sense that it describes the spatial distribution of energy associated with the electron, seems like a valid and pretty insightful conceptual leap, even if it's definitely not a classical field in the old-fashioned sense.
So here's a final thought to leave you with, inspired by that QFT perspective in the source. If you really accept that view, that what we call an electron isn't a tiny particle in space, but rather a persistent pattern of energy of a field that fills all of space, does that change your fundamental understanding of what matter or even what a particle really is? Something to ponder.